If humans build a colony on Mars, what will they look like in the future? The day we set foot on Mars, humanity begins to split in two. When the first Martian baby is born, will the word human still mean the same thing? We'll have to change to survive on Mars. The question is, how much will we change? Because Mars tries to kill us, and evolution changes us to keep us alive. So today, we're speeding things up. In our heads, we're putting evolution on 2 times speed. We'll use 10,000 years as a symbolic shortcut, an accelerated crash course in adaptation. Meet Carl, one of the first colonists heading to Mars. Now we're going to compare the physics of Earth and Mars. One rule at a time, and explore how those rules could gradually reshape the human body. Walking on Earth is easy because the human body is calibrated to gravity. On Mars, gravity is lower, 0.38 g. It sounds like, meh, not a big deal. But for the body, it means resetting all the settings. Carl is still Carl, but Carl's born on Mars would probably say, "Why am I carrying bones this heavy?" When the load decreases, bones don't need to stay thick. Muscles stop chasing bulk and start chasing efficiency. The result? A taller, thinner, lighter body, especially the legs. And here's the funniest part. The walk changes. On Earth, walking is an incredibly efficient mechanical trick. On Mars, that trick partly breaks, and humanity discovers something unexpected. Sometimes hopping makes more sense than walking. Yes, the Martian walk would most likely not be a smooth stride, but a light, bouncing, hopping gait. Now we arrive at the most painful truth about Mars. Breathing outside is simply impossible. But here's the twist. The problem isn't that there's too little oxygen. The real problem is that there is almost no pressure. On Earth, atmospheric pressure at sea level is about 101,325 pascals, 1 atmosphere. On Mars, average surface pressure is around 600 pascals, and that's less than 1% of Earth's pressure. No matter how strong or super your lungs are, physics steps in and says, this violates the rules. Breathing isn't just about oxygen existing, it's about pressure pushing air into the lungs. On Earth, every breath works because external air pressure is higher than the pressure inside your lungs, so air flows inward naturally. On Mars, the pressure is so low that air simply doesn't get pushed into the lungs at all. In fact, at such low pressure, the air is too thin to fill the alveoli. Oxygen molecules are too sparse to create effective gas exchange. Bodily fluids would begin to boil at body temperature, a condition known as ebulism. So humans on Mars cannot breathe in the traditional sense. Air would have to be actively pumped into the body by technology. In that sense, we could call it a cyborg civilization. Early colonists would walk around with massive backpacks. Then technology would shrink. Belt-mounted modules, chest units, closed-loop oxygen systems, and 10,000 years later, these systems would become invisible. Not tools, but infrastructure. On Earth, people say, my phone battery is dead. On Mars, they'll say, my oxygen cycle is dropping. Mars is about 52% farther from the sun than Earth. As a result, the total sunlight reaching the Martian surface is only about 43% of what Earth receives. The reason is simple but fundamental. Light, like gravity, follows the inverse square law. Its intensity decreases with the square of the distance. So if you move twice as far from the sun, the light doesn't drop by half. It drops to 1/4. That's exactly what happens in the case of Mars. So yes, there are days. There are shadows. But it's as if the sky has a permanently dimmed switch turned on. Then comes the ironic and dangerous part. Mars has an extremely thin atmosphere. On Earth, the atmosphere, especially the ozone layer, filters out most harmful UVB and UVC radiation from the sun. On Mars, however, the ozone layer is nearly non-existent. Atmospheric pressure is less than 1% of Earth's. As a result, less total light reaches the surface, but the ultraviolet fraction of that light is much higher. So on Mars, the sun seems to say, I'll light less, but I'll stare harder. This directly affects the eyes. To survive on Mars, the ideal eye wouldn't chase ultra-high resolution, but would instead evolve to collect more photons. Hey, that creates evolutionary pressure toward slightly larger eyeballs, a wider retinal surface, photoreceptors more sensitive to low light, and yes, over long timescales like 10,000 years, it's reasonable to expect eyes to become a bit larger and rounder. Relax. This doesn't mean giant anime eyes, we're talking millimeters, not centimeters. So, wave hello to Carl, with slightly bigger eyes. Earth is surrounded by a vast, invisible shield. The planet's liquid metal core is in constant motion, and as a result, it generates a powerful magnetic field. Mars, however, lost this internal dynamo about 4 billion years ago. Earth's magnetic field acts like a magnetic umbrella, deflecting a large fraction of charged particles from the sun and cosmic radiation before they even reach the atmosphere. The difference between Mars and Earth is not just a matter of weakness. It is a fundamental structural difference. The short answer is this: Mars today has no global magnetic field. If Earth's global magnetic field is taken as a reference, Mars's magnetic field is less than 1%, as strong. And even that remaining field is not continuous, not global, but limited to localized remnants trapped in ancient rocks. On Earth, the umbrella is open. On Mars, only the metal ribs remain. As a result, high-energy particles from space reach the Martian surface far more easily. The atmosphere cannot slow them down sufficiently, and the magnetic field cannot bend their paths away. And in this environment, natural selection stops caring about muscle. Instead, it asks, whose cells are more resilient? Whose DNA repairs itself better? Because the real threat is not physical load, but radiation that pierces the cell nucleus. In 10,000 years, humans do not become superheroes, but the direction is clear. The body begins to invest in stronger DNA repair mechanisms, faster removal of damaged cells, a more protective outer layer. And this change becomes visible in the skin. On Mars, skin is not shiny, thin, or delicate. It becomes more matte, thicker, and less permeable. What you feel when you touch it is not softness, but durability. And skin color. It does not turn coal black. Because visible light on Mars is already limited, the body seeks a balance, protection from UV radiation without sacrificing too much of the available light. That balance pushes skin tone not to an extreme, but toward olive shades. Not too light, not too dark, a middle tone that filters radiation without wasting precious photons. When you look at a Martian human, you sense this immediately. This body is not built for strength, but for cellular survival. And yes, Carl, with his new skin tone, will be truly striking. A Martian human could end up looking eerily similar to the alien we know from pop culture. But that wouldn't be about some alien gene, it would be about physics. Because even our bodies on Earth weren't simply born this way. Over time, they were slowly shaped by planetary conditions like gravity, atmosphere, light, and the protection of a magnetic shield. So here's the strangest and most unsettling question. Were we Earth humans from the beginning? Or did Earth teach us the shape we wear? Maybe what we call an alien isn't a completely different species from another star at all. Maybe it's just a human still being rewritten by the rules of a different planet. If you enjoyed this video, don't forget to subscribe to our channel and hit that like button and share it with the people you care about, so the light of science can reach everyone.